Thank you. Yeah, so I'm Thilina. I'm going to present my work on negative sampling techniques for dense passage retrieval in a multilingual setting. Not okay. Yeah, so this is a reproducibility work that I did with Yates and Maarten Rijke. Let's start. So this is the typical architecture that we use for dense passage retrieval. It's a dual encoder model. Here we have two transformer models, one that we use to encode queries, one that we use to encode passages, and we get dense representations for the query, for the passage. And the nice thing about this setup is that the two encoders are distinct, meaning that we can pre-compute all the passage and document representations, and then when a new query comes along, we just use the query encoder to generate a representation for the query, and then we use approximate nearest neighbor methods to find the most similar or most relevant passages or documents from the collection for the query. And if you look at how we train these dual encoder models, usually we have data that comes with query and positive passage pairs or query and relevant passage pairs. And we use a contrastive learning setup to train the model. And you can see the loss function below, but the takeaway from the loss function is just that we need to maximize, for a given query, we need to maximize the similarity between the query and the positive passage. And we need to minimize the similarity between the query and negative passages. But our data sets usually come with just queries and positive passages, so we need a way to find these negative passages. There are many different methods that have been proposed in the literature, and the general idea is that we want these negatives to be hard. And what that means is we want it to be challenging for the model to recognize, to distinguish between the negative passage and a positive passage. So that's why we call them hard negatives. And there's many different methods that you can use to do this. We will look at some of these methods and how they work in a multilingual setting. Now I'm going to try and define what my flavor of multilingual retrieval is. So first of all, what we do in this paper is we take existing negative sampling methods that are usually tested in an English language setting. We take them to this multilingual setting, and we see whether they are still effective, whether they still work the same way. And then as a bonus, we also take a couple of existing methods, combine them, form a new one, and then see if that does any better. So the multilingual part, first of all, the model. It's a multilingual model, meaning for us, it's the same model that can do retrieval in multiple languages. So it's trained to perform retrieval in multiple languages. And then we test this model in a monolingual retrieval setting, which means for a given data set, the queries and the passages are going to be in the same language, but we have multiple data sets from multiple languages. So for individual data set, it's the same language, but we have multiple such data sets from multiple languages. If we categorize the data sets, the test data sets that we use under three settings. First of all, we have the in-distribution setting, where the model is trained to do retrieval in that language, so it's a known language. And then the test set and the training set are they follow the same distribution, so they look similar. And then we have the out-of-distribution setting, where the language is still known, so the model is trained to perform retrieval in that language. But now the test set is different, or it has a different distribution to the train set, so we call that out-of-distribution. And then finally, we have the zero-shot setting, where the model is not trained to do retrieval in this language, so it's an unknown language, and the distribution is different between the train set and the test set. And for each of these settings, we have multiple data sets, which we will see later on. Now let's take a look at the negative sampling methods that we look at in this paper. So first off, we have the most simple, straightforward method, which is in-batch negatives. Here, what we do is you take, for a given query in a training batch, you just take the relevant passages or the positive passages for the other queries in the same batch as the negatives for a given query. So that's basically random negatives, meaning that however your framework builds a training batch, that's what your negatives are going to be. Going beyond that, we can look for hard negatives instead of relying on random negatives, which tend to be too easy. So the first method we have is to use BM25 to find the negatives. So here, for each of the training queries, we use a BM25 model to build a ranked list of passages, and then we sample from the top 100 of this ranked list to find passages that are that BM25 thinks is somewhat relevant to the query, meaning that they're likely to be hard negatives. And then going beyond that, we also have another method introduced in the paper ANS. So this is a hard negative mining method where the dense retrieval model that is being trained itself is used to find hard negatives. So instead of using an external model like BM25, it uses the model that is being trained itself. And the advantage of doing it that way is that as the model is trained and as the model improves, we can iteratively update the hard negatives so that we don't get to a point of the hard negatives becoming easy negatives for the model, because we continuously update them. And then finally, we have clustering using a teacher model. This was introduced in the topic-aware sampling paper. Here, what they do is they take a teacher model to generate representations for either the training queries or the training passages, and then they cluster those representations. And to build a training batch, they sample from a single cluster, and the effect of doing that is you end up with a training batch that contains similar queries or similar passages. And then if you just use in-batch negatives, you end up with negatives that are likely to be hard for the model just because they are similar to each other, because they're sampled from the same cluster. So those are the existing methods that we look at. And here it is in a table form. Next, we have the method that combines intuitions from the task approach and the answer approach, which we call iterative clustered training. So just like tasks, we use clustering to place queries and passages, similar queries and passages in a given training batch. But unlike tasks, we don't use an external teacher model to do the clustering step. We use the model that we are training, so the dense retrieval model itself, just like ANS, to generate the representations and then do the clustering. And then again, similar to ANS, this means that we can iteratively update the clustering as we go on. So as the model learns, we update the clusters and then we build new training batches. So again, the hard negatives remain challenging as the model is being trained. Compared to ANS, we need less compute to do it, to use this technique, because ANS uses the entire collection, so it mines the entire collection for hard negatives, while iterative cluster training only uses like the training queries or the training passages. So if you add this method to the table, now we have the in-batch negatives at the top, BM25, and then we have two flavors of tasks. So that is simply clustering on queries and clustering on passages. And then we have ANS, and then we have the two ICT methods where we again cluster on queries and cluster on passages. So if you look at the process that we follow for the paper, to train the models, we have two steps. So this is following existing work in the area. So the first step is we use a pre-fine-tuning step to train the model on retrieval in English, and then we fine-tune on a combined data set of all the languages that we have. And then for evaluation, of course, again, we look at the three settings: in distribution, out of distribution, and zero-shot. And then if you look at the actual data sets that we use at each stage, first off, during training for pre-fine-tuning, we use MS Marco. And then for fine-tuning, we use the training sets from the Mr. Tidy dataset collection. And then during testing in distribution setting, we use the test sets from Mr. Tidy, so that's in distribution. And then for out of distribution, we take the languages from M Marco that also appear in Mr. Tidy. So that is, these are now known languages for the model. And then for the zero-shot setting, we take the languages from M2.4 that are not in Mr. Tidy. So now these are languages the model has not been trained to do retrieval on. And then we also include a few other IR data sets in languages that the model is not trained to do retrieval on. And then if we look at the model, like the pre-trained weights that we use for our models, all the dual encoders are initialized from mbird. So this is a multilingual version of BERT. And then for the task method specifically, we need an external teacher model. So for the English pre-fine-tuning step, we use a distilled BERT model fine-tuned on MS Marco. For the fine-tuning step on all the languages, we use a model that is trained on all the languages from Mr. Tidy. And then we also include BM25 as a baseline in our results. Speaking of, so the first result was a little surprising for us in this distribution setting, because in English, normally what we see is that more complicated negative sampling methods like ANDs work better. But in this case, we saw that DPR with using BM25 negatives, so dense passage retrieval using BM25 negatives outperform the other negative sampling methods. But then when we come to the out of distribution results, we see that the BM25 negatives are no longer good enough, and the ICT method outperforms the other negative sampling methods. This is also true for the zero-shot results on M2.4, but when we go to the other zero-shot datasets, which are out of distribution, unknown language, and also out of domain, actually, we see that BM25 outperforms all the dense retrieval methods, which tends to happen when you go far out of domain. But comparing the negative sampling methods, our ICT method still outperforms the other methods. So in summary, in distribution test sets, we saw that BM25 negatives actually outperform other negative sampling methods. But in the other settings, ICT does better. And also we saw that for the two clustering methods, TAS and ICT, if you clustering on passages tends to work better than clustering on queries, usually because the passages contain more information and you can do the clustering step better. Finally, if you look at the generalizability of English findings to the multilingual setting, the general findings still hold when we move to the multilingual domain. That is, using negative sampling methods gives a significant improvement over simply using in-batch negatives or random negatives. And then we also saw that iterative methods are more effective. That is, the direct comparison between ICT and TAS. Because ICT continuously updates the negatives, it tends to outperform TAS, and it also outperforms ANDs while being more efficient to train. So finally, our recommendations. If you are going to use the dense retriever mostly on in-distribution data, we recommend just using BM25 negatives. It's fast and easy to do, and it gave the best results in our experiments. For anything else, if you need your model to work on out-of-distribution data, then we recommend iterative cluster training with a slight caveat. If you need it to work on completely different looking data, maybe BM25 is still the better option. And that is the end of the presentation. Thank you.